Hey, welcome to Physics 1403, Stars and Galaxies. So I want you to imagine that Sir Isaac Newton, the guy who figured out how about 90% of physics works, has a problem. So Isaac Newton viewed the universe as being very flat, uh, being very infinite, and having an infinite number of stars. The problem with this view is that it doesn't fit the observable universe. Under Newton's ideas, then two things are going to happen. Number one, even an infinite number of stars are eventually going to be drawn together into one big giant star blob because of gravity. Remember that gravity has no end to how far it can reach. And while, yes, it's very weak the farther away you go because of the inverse square law, it is still there. And so if you have an infinite universe with an infinite number of stars, eventually they're all going to be pulled into one place. What's more is if you have an infinite number of stars in an infinite universe, why is the night sky dark? There is no place that you can look that you're not eventually going to see a star. Even if that star is billions of light years away, if we live in an infinite universe, that star should eventually, the light of that star should eventually reach the Earth. And so the night sky shouldn't look like the night sky. So we call that Olber's paradox after a 16th century physician, or we call that Olber's paradox after a contemporary of Newton who wrote him a letter asking him that very question. By the way, Newton didn't have an answer. Another famous physician was Albert Einstein. Now, he didn't view the world, space-time, as being a fixed quantity. He viewed the universe as being full of space-time that is flexible. Under his theory of relativity, space and time were the same thing. And the faster you move through space, the slower you move through time. And if you wanted to move through time as quickly as possible, don't move, because the exact opposite is if you're not moving, if you're still, you're moving through time as quickly as it's possible to do. And he viewed gravity as a supermassive object, in this case a planet, that distorts that space-time, in essence forming almost like a divot on a rubber sheet. In fact, it's sometimes called the rubber sheet model. The problem with this model is, once again, why hasn't the universe collapsed in on itself? These divots, if the universe is full of divots from high mass stars and planets and moons and golf balls and whatever, even the smallest divot, they should eventually collapse. This was such a problem to Einstein that when he was writing his papers, he made up an idea called a cosmological constant. The symbol for it almost looks like an upside down V. He called it his greatest mistake because he couldn't mathematically prove it, but it had to be there or all of his equations would collapse. Apparently, if the universe is big and full of massive objects, you needed some force pushing against all of those objects. Otherwise, they were going to collapse in on themselves. Another astronomer of the 20th century was Edwin Hubble. And Edwin Hubble noticed something that was significant. He noticed that the universe was not static like Newton or like even Einstein believed. He realized through looking at spectroscopy that distant galaxies were all redshifted to some degree. And what's more is he realized that the further the galaxies were from us, the more they were redshifted. This led him to the conclusion that we were living in a universe that is in a constant state of expansion. And when he does the math, he comes up and he realizes that there's something called, we now call the Hubble constant. And that is the rate at which we can predict that these galaxies and these clusters and superclusters are all moving away from us. All right. And while some people have tried to tie that to Einstein's cosmological constant, he did not try to make that connection, but many people have. So what's going on here? Well, what's going on is that we're living in an expanding universe. Then if you take that universe, as Hubble did, and you rewind the clock, if you look at the Hubble constant, which is about 73, and you rewind it, then you start realizing the galaxies start getting closer and closer together. And you continue to rewind it until you finally realize that all the galaxies and all the mass and everything that we can detect in the observable universe eventually ends up at a single point. We call this theory and the resulting explosion or inflation of the universe the Big Bang Theory. All right? And while there's a lot of, I'm going to say, misconceptions about the Big Bang Theory, I just want to address a couple things. Number one is I want to address what a theory is versus a law. And then I want to look at some of the most important pieces of evidence that we have available in support of this theory of the Big Bang. First of all, there are a lot of people who will say, well, if there was any evidence, it would be a law. And that's not how science works, okay? A law explains what happens. For example, there is a Hubble's law that explains what we will observe based on the distance to a galaxy from where we are and how we can use that law to explain what behavior we will observe. So it answers the question of what. Theories are messier. They answer the questions or attempt to answer the questions of why. In other words, Hubble's law says this is the movement of this galaxy. The Big Bang Theory is, why is that galaxy moving at all? And why do we see some of the things that we see in the universe? And that is what I would like to look at, is evidence. Theories in science, in order to be labeled a theory, it is highly tested. It is generally accepted as accurate if it can be used to predict future outcomes, or it can be used to predict future observations. And that is definitely the case with the Big Bang Theory. All right, but what are some of the evidence that we have for the Big Bang Theory? Well, I want to talk about three of them real fast. The first piece of evidence I want to look at is redshift. This is what Hubble is talking about. This is what he is observing. The more distant these galaxies are, the greater the redshift is. And so what we see is that a galaxy that's relatively close, a couple million parsecs away, is not shifted nearly as far as a galaxy that is several million parsecs away. All right. What's causing that is twofold. Number one, the galaxy itself is in fact moving away from us. Okay, and that's going to cause some redshift. But this is a greater amount of redshift than even from movement. And under his cosmological concept, and as our understanding of the Big Bang is, that the galaxy itself, yes, is moving, right? But what's really happening is that space itself is expanding. All right, and so imagine writing your name on a rubber band, and then taking that rubber band and stretching that rubber band, and as it stretches, look at what the words on that you wrote on that rubber band do. They get long and stretchy. That is the sort of what we call cosmological redshift that we're talking about with the Big Bang. This photon has already been emitted. So it's not being redshifted anymore by movement, because that's already happening. But because of its distance and because of the time it takes us to get here, all right, it continues to be redshifted by the stretching out of space-time that it is traveling through. So it continues to be redshifted. Otherwise, a redshift from any distance should be the exact same as long as those objects are moving at the same speed. And they're moving at the same speed relative to ourselves. But instead, an object that is moving however many millions of miles per second, but long ways away, is redshifted even greater than that same object would be if it was closer. So that stretching of space-time. I think that's one thing people don't understand about Big Bang. The Big Bang Theory is that space itself is getting bigger. It is not that everything's flying out into nothingness. There is no nothingness out there. Instead, the universe itself is getting bigger. And the reason why galaxies aren't getting further apart is because we're held together by gravity. And the force of gravity, as weak as it is compared to other fundamental forces, is still greater than the force that comes from this expansion. Nevertheless, this red shift that we see, particularly the more distant objects, is an important piece of evidence for the Big Bang. A second piece of evidence has to do with hydrogen. All the hydrogen in the universe comes from the Big Bang. And there is a mathematical model that says that about 90% of the hydrogen should have been, well, just basic hydrogen. One proton, one electron orbiting that lone proton. But there should have been about 10% of the hydrogen made. It's something we call deuterium. It's an isotope of hydrogen that has one proton and one neutron. Still has that one electron going around. Chemically, it behaves exactly the same as any other form of hydrogen, except that this hydrogen, this deuterium, hydrogen 2 as it's sometimes called, is formed only in the core of very hot, deep stars. Okay, then why do we find it all over the universe? When we look at gas clouds that are billions of years old and that are producing stars, they're stellar nurseries. They're not the result of dead stars. They're new stars or new proto-stars. And yet we still find this huge amount of detectable amount of deuterium. And so the evidence that what this is saying is that in the primordial craziness of the first few seconds of the Big Bang of our brand new universe, that it was hot enough that in essence it was the same temperatures and conditions that were similar to what we see inside of stars today. And that would have produced deuterium from free electrons or from free neutrons and free protons, something a process called neutron capture. And that is an important piece because it helps to explain why we find deuterium where it shouldn't be. It's not near a star, it's not near a supernova remnant, it's not near a planetary nebula, the sloughed off parts of a star, of an intermediate mass star, anything like that. It's just out there in space in the gas clouds, that the interstellar media. And the last piece of evidence I want to look at is this picture right here. This is what we refer to as cosmic microwave background radiation. The idea is that if the universe expanded into existence in Big Bang, there should be some direct evidence. There should be some sort of, like redshift and deuterium, those are indirect evidence. But there should be something that's that big that there should be some sort of background radiation that still exists to this day. All right, remember that a universe or a star or anything really, when it's highly compact, is going to be very hot. And so as it expands, it should cool. But you should still be able to detect that. Well, lo and behold, we can. This is actually taken from the COBE satellite, and it is cosmic radiation. It is in the microwave wavelength of the electromagnetic spectrum. It demonstrates that our universe has an average temperature of about 3 Kelvin. That's negative 270 degrees Celsius for those people who are keeping track of it. It's not a friendly environment, right? But this is the most direct piece of evidence that we have because this isn't in one place. This isn't like, well, that's the remnant of a supernova. Well, no, because it doesn't matter where we aim our radio telescopes, we still find the same background radiation. So there you have it. 3 pieces of compelling evidence that demonstrate the validity or that support the validity of the Big Bang Theory. And as we discover more evidence, as astronomers get out there and with better viewing instruments or better computer models, The Big Bang Theory, like any other theory, is subject to adjustment. All right? But as it stands now, the Big Bang Theory is the best theory to explain cosmological redshift, all that deuterium that we're seeing out there, and all this background radiation that we are seeing out there. And so that is why the Big Bang Theory is considered such a robust and valid theory because it fits the evidence. Now, in the future, if we find some new piece of evidence, it may change everything. That's the nature of science. You know, that's the difference between science and dogma, is that they look at science, they should look at evidence and go, okay, does this fit our theory? And if it does, then that's great. And if it doesn't, well, that's great too. We get to rewrite a theory, or we get to abandon a theory and find a better theory, whatever it is. But that is the joys of science, and that's the joy of astronomy. So until then, I'll see you in class. Have a great day.